Welcome to the deep dive. Anyone who's ever touched network management knows that, well, the firewall is kind of the cornerstone of security. It's been that main line of defense, really, since the early 90s.
Absolutely. And it's crucial to see the firewall for what it fundamentally is, an access control mechanism. For years, the thinking was pretty simple. You had your internal network that was the trusted zone, and then everything else, the internet, was inherently untrusted.
Right.
What's really shifted now, though, is how that whole internal trust idea is basically fading away. We're moving necessarily towards zero trust.
Exactly. And if you can't automatically trust your own network anymore, well, how do you decide what traffic gets in and what gets blocked? So that's our mission for this deep dive, really getting into the nuts and bolts of how firewalls make those critical decisions.
The decisions to accept or DDNY traffic.
Precisely. We'll be looking closely at the rule sets, best practices for architecture, and maybe some of those common slip-ups, the pitfalls that can mean a system designed to DDNY traffic accidentally ends up configured to allow it.
Yeah, those subtle mistakes can be dangerous.
Okay, so let's start by mapping things out a bit. When we say firewall, maybe we shouldn't just picture a physical box. It's more of a function, isn't it?
That's a great way to put it. It is a function. It's about isolation. And that function, well, it can be implemented as what some call a bump in the wire. That's your traditional standalone box, physical or virtual, sitting in the path of the traffic.
Okay.
Or it could be a bump in the stack, basically software running right on a computer's operating system, protecting just that one host.
Got it. So different forms, but the same job.
Exactly the same job. Isolating risk zones.
And a risk zone is just any part of the network with a certain level of risk, or inversely, trust.
That's it. Simple concept, really. We typically think of the big ones. The internet, highest risk, obviously. Your private network, ideally, the lowest risk. And then maybe a DMZ, sort of a go-between zone.
Right, the demilitarized zone.
And if you look at how seriously some organizations take this, like the Canadian Center for Cybersecurity, they have quite formal definitions for these zones to ensure proper compartmentalization. It underlines that modern networks aren't just inside versus outside anymore.
Okay, so what are their categories?
Well, they start with the public zone, the PZ, that's the internet, basically, highly hostile.
Assumed hostile, yeah.
Then you've got the public access zone, or PAZ. Think of that as your DMZ, a buffer zone. It's where you put things that need to face the public internet, like web servers, maybe VPN endpoints, proxy servers.
Makes sense. Shielding the inside.
Then moving further in, you have the operations zone, OZ. That's your standard internal network where most users and their systems live day to day. Your typical LAN or internal wireless.
Okay, the main work area.
And finally, the restricted zone, RZ. This is for the really critical stuff, sensitive data, essential business services. Access here needs to be super controlled, heavily authenticated.
That sounds like a lot of zones, a lot of boundaries to manage. Is all that segmentation really worth the administrative effort?
It definitely adds complexity, no doubt, but the strategic payoff is usually huge. First off, compliance. Think about PCI DSS or IPA. Segmenting means you might only need to apply those really strict controls to your restricted zone, not the entire network. That saves a massive amount of effort and costs.
Scope reduction, okay.
And second, security. It limits how far an attacker can move laterally if they do get in. It contains breaches. It also reduces the overall attack surface because you're only allowing the absolutely necessary traffic to cross between these zones. Everything else is blocked by default.
Okay, so segmentation sets the stage. Now let's talk about the original tool for enforcing those boundaries.
Yeah.
Static packet filtering. Just looking at packet headers, right? Layer 3, layer 4 stuff.
Exactly. The real basics. It checks things like the protocols TCP, UDP, ICMP. It looks at the source IP address, the destination IP address, and typically the destination port number, like port 80 for web traffic.
And the most important piece.
The action. Based on those header details matching a rule, the firewall has to do something. It either needs to explicitly accept the packet, let it through, or explicitly DDNY it, block it, drop it.
Accept or DDNY. That choice really defines the firewall's whole security stance, doesn't it? Which leads to those two core philosophies for writing rule sets.
Precisely. You've got the DDNY by default, allow by exception approach. This assumes everything is bad unless you specifically say it's okay. You create rules only to allow the traffic you need.
In the other way.
The other way is allow by default, DENY by exception. This assumes everything is fine until you specifically block something. Much riskier.
Now, you always hear that DDNY by default is the only way to go for security. It forces you to think about every connection you're allowing. But doesn't that create a bottleneck? Like, if developers need a new port open, they hit a wall until an admin writes a new allow rule. It seems like it could slow things down.
Oh, it absolutely introduces friction. There's no denying that. It's a trade-off. But from a security perspective, the benefit is usually considered non-negotiable. DENY, by default, is the recommended standard pretty much everywhere.
Why so definitively?
Because it provides a crucial safety net. Any traffic you didn't think about, any potentially malicious connection you didn't anticipate, just gets dropped automatically. The operational friction you mentioned, that's often seen as the necessary cost of doing security properly. You should only ACE accept what you absolutely know you need.
Okay, fair enough. But static packet filtering, just looking at headers, it had its limits, right? It didn't really understand the conversation between two machines.
Exactly. That was its big weakness. It looked at each packet in isolation. It couldn't easily handle things like fragmented packets where one message is split into multiple pieces. And critically, it couldn't look inside the packet at the actual data or payload. Which meant if an attack was hidden inside seemingly legitimate traffic, the static firewall was blind to it. That inability to track the conversation state led to the next big evolution, stateful inspection, sometimes called dynamic packet filtering.
Stateful. So it tracks the state of a connection.
Yes, that was the breakthrough. Instead of just checking individual packet headers, a stateful firewall monitors the entire communication session. For TCP, for example, it watches the three-way handshake that starts a connection. It keeps a table of active, legitimate connections.
And the big win there for administrators.
Huge simplification of the rule set. Think about it. If one of your internal users connects out to a web server and your rule explicitly allows that outbound connection, the stateful firewall notes that session when the web server sends packets back.
Ah, the firewall knows it's part of that established session.
Exactly. So it automatically allows the return traffic. You don't need a separate complex rule just for the replies. It practically halves the number of rules you might need compared to static filtering.
That's a big deal. What about protocols that don't have connections, like UBP or ICMP?
Good question. For those, stateful firewalls kind of simulate a state. They'll allow a reply within a certain time window after an outgoing packet. It's not perfect, but it works reasonably well.
But even stateful inspection isn't looking at the data itself, right? If malware is tucked inside an HTTP download, that's part of an allowed session.
The stateful firewall will likely ACE accept it, yes. Because the session state looks fine, the ports match the rules, that's where the next level comes in. Things often bundled into modern firewalls like application proxies or application-level gateways.
Okay, so what do they do differently?
They go much deeper. An application proxy actually understands the specific application protocol like HTTP or FTP. It intercepts the connection, often terminates it, inspects the payload, the actual data, looking for threats or policy violations, and then establishes a separate connection to the destination, forwarding the data only if it's clean. It's like a very thorough middleman.
Much more intrusive, but much more visibility.
Precisely. And beyond the filtering technology itself, the overall architecture matters too. Are you relying on just one firewall?
The single firewall approach. Cheaper, simpler, maybe?
Cheaper, simpler, but also a single point of failure, both for connectivity and security. If that one box gets compromised, your whole defense might crumble.
So the alternative is?
A dual firewall architecture. Often you'll see this with a DMZ sandwiched between two separate firewalls. One faces the internet, the other faces the internal network. An attacker would need to compromise two distinct devices, potentially from different vendors, to get all the way through.
More secure, but sounds more expensive and definitely more complex to manage, especially the rules.
Exactly. More rules, more devices, more chances for misconfiguration, which brings us neatly to the really tricky part. Rule order.
Right, because most firewalls use a first match apply system. The first rule on the list that matches the traffic dictates the action, and the firewall stops processing right there. Rule 50 might say DNY, but if Rule 1 says accept for the same traffic,
Rule 50 never even gets looked at. The traffic is accepted based on Rule 1. This means the order of your rules is absolutely critical.
so what's the guiding principle for ordering?
Specificity first. Your most specific rules need to come before your more general rules. If you have a rule to DNY access from one specific IP address to a server, that rule must come before a general rule that might allow access from the entire subnet that IP belongs to.
Otherwise, the DENY gets ignored.
Correct. And when you get the order wrong, you start running into what we call rule anomalies. These are logical problems in the rule set, and they can completely undermine your security policy.
Okay, what's the worst offender?
Probably the shadowing pattern. This is a flat-out error. It happens when one rule, let's call it rule X, matches all the possible traffic that a later rule, rule Y, could possibly match. And crucially, they have different actions. Say, rule X is an allow and rule Y is a DNY.
So rule Y is completely hidden, shadowed by rule X.
Exactly. It's unreachable. Any traffic that should have been denied by rule Y gets accepted by rule X first. This is a major security hole. The fix, swap them. Put the more specific rule, often the DNY rule in this case, first.
Makes sense. Okay, what's another common one?
The correlation pattern. This is a bit more subtle, maybe more of a warning flag than a critical error, but it needs careful checking. It happens when two rules partially overlap in what they match, but they have different actions.
Partially overlap. How so?
Okay, imagine rule A accepts traffic from, say, subnet 1 going to server Z. But rule B denies traffic from a specific host within subnet 1 going anywhere. For traffic from that specific host to server Z, both rules match.
Ah, so the outcome depends entirely on which rule comes first.
Precisely. If rule A is first, the traffic is accepted. If rule B is first, it's denied. The order completely changes the result for that overlapping traffic. It's not necessarily wrong, but the administrator must verify that the current order matches the actual security policy intention.
Got it. That sounds like a potential source of confusion. What else?
The third big one is the redundancy pattern. This looks harmless at first glance. It's when a later rule is made completely irrelevant because an earlier rule with the same action already covers all its cases.
So like Rule 6 ACCEPts all traffic from subnet 1, and Rule 7 also ACCEPts traffic from a specific host within subnet 1.
Exactly. Rule 7 is redundant because Rule 6 already accepted that traffic. Why care? Well, maybe one redundant rule isn't a big deal, but imagine a firewall with thousands of rules.
Performance hit.
Performance hit, definitely. Each packet has to be checked against more rules than necessary, adding latency. But maybe worse is the administrative overhead. Trying to troubleshoot a problem in a rule set bloated with redundant rules is a nightmare. It increases complexity and the chance of errors during changes. The recommendation, keep your rule set lean. Remove redundant rules.
Good advice. Clean rules are happy rules.
Something like that, yeah. There are other minor issues too, like generalization, where you might have overly broad allow rules or irrelevance, where a rule exists but doesn't actually match any traffic that ever passes through that firewall. But shadowing, correlation, and redundancy are the big three anomalies caused by ordering issues.
Okay, this has been quite the journey. We've gone from the high-level concept of risk zones down through the basic filtering actions, accept, DN, allow, and into the really critical nitty-gritty details of rule ordering and how getting it wrong can inadvertently flip a D and NY into an allow.
And I think the key thing to grasp now is the broader philosophical shift happening. For decades, firewalling was primarily about interzone control, protecting your trusted internal zone from the untrusted internet, guarding the perimeter.
Right, building the walls higher between zones.
But zero trust thinking completely changes that. It says perimeter control isn't enough because you can't inherently trust any zone, not even your internal operations zone.
Which leads us perfectly into that final thought we want to leave everyone with. If the operation zone, the OZ, is supposed to be the relatively safe space for internal users and systems, why is monitoring intrazone traffic moving within the OZ suddenly so critical for modern security?
It's critical because we now recognize that threats don't just come from the outside. They very often originate inside, perhaps from a compromised user machine within that supposedly safe OZ, or an attacker gets one foothold inside and then moves laterally.
Ah, moving sideways within the same zone.
Exactly. And traditional firewalls focused on zone boundaries are often blind to that lateral movement within a zone. So the zero trust answer is that the firewall's core philosophy, DENY by default, allow by exception, needs to be applied internally too. You need segmentation within zones and monitoring of traffic flows even between machines that are supposedly in the same safe area. That internal visibility, dealing with threats already inside the wire, that's probably the biggest firewall challenge today.